Presenters.
Hi, everyone. I'm Alyssa Scordo. I'm a hydrologist at BGC, and I'm excited to introduce our next symposium topic and our presenters, Patrick Grover and Evelyn Moorhouse, that will speak today on the next generation of hydrologic assessment tools in Cambio. The need for better assessment and monitoring tools really started to build at BGC following a major flood event in Alberta in 2013. During this event, the region experienced several days of heavy rainfall and catastrophic flooding. From this, we really recognized a need to develop real-time flood monitoring for pipeline infrastructure that could alert operators during a major event as part of our overall Cambio geohazard management program, which was introduced in our last presentation. Today, this program is used by pipeline operators across North America to trigger emergency response plans, such as shutting in a pipeline to reduce the risk of pipeline failures and impact to the environment during a flood. With over 10 years of development, BGC continues to advance hydrologic tools such as real-time flood monitoring through the efforts of BGC's Cambio software teams, of which Patrick and Evelyn are active contributors and innovators. Evelyn is a geoscientist in training who holds a master's degree in data science and spends her time working on Cambio development projects with BGC's software and data science teams. She joined us after working on a UBC capstone project that was supported by BGC through the Master of Data Science program at UBC. And Patrick is a principal hydrotech engineer that provides directions to BGC's software and data science team using his extensive background in hydraulics, software development, and scientific computing. I'm fortunate to work with Patrick on our surface water team and always learn so much from his mad scientist ways. Please welcome Patrick and Evelyn.
Thanks so much, Alyssa. I'm sharing, so just let me know if there's any technical difficulties, but I'm going to assume we see my screen and all is good to go. Alyssa also already gave a great Cambio introduction, but I just wanted to highlight that we now support sectors beyond pipelines, and we work with a ton of different geohazards, but today we're focusing on hydrotechnical hazards and flooding in particular. So we're going to be talking about two ways that we're improving Cambio kind of in two main groups. So the first is site characterization and then real-time monitoring. So for site characterization, that's the process of BGC employees going out into the field and collecting a whole bunch of data for site attributes to get an understanding of what is going on at a river at a certain location. And so usually in terms of our pipeline clients, this location is the intersection of a pipeline with the river. So some of the things we figure out are, for example, depth of cover. So if the pipeline is running underneath the river, how much material is in between the bed of the river and the pipeline? And by finding out all of these different site attributes, we're then allowed to determine what is the flow that we would expect to see that would remove enough material from the riverbed to expose the pipeline. And then by determining that magnitude of flow, then we can set corresponding thresholds for our real-time monitoring. So we use gauges that are actively reading discharge and flow at rivers, and we process those readings every 15 minutes. And if a threshold is surpassed, then we send an alert to our clients. So this is kind of what our front-end users and our clients see with regards to hazard management, but there's a really important part of this that goes on kind of behind the scenes internally at BGC, which is the flood frequency analysis that we need to do for gauges and sites for all of this to work. So really quickly, if you don't know what flood frequency analysis is, it's just looking at historical data where we have it, so at a gauge, over time, and looking at the historical annual maximum discharge, and then using that information to figure out the probability of seeing a certain volume of flow or discharge every year. So for a certain gauge, there might be a 10-year return period corresponds to a flow of 100 meters cubed per second, and that means that any given year, there's a 10% chance we'll see that volume of flow. So we do that where we have historical data at gauges, but we have ways to then model and determine the same process and create a flood frequency analysis at a site where we don't have a gauge. So there's no way of measuring flow upstream or downstream. It's a channel that has no measurements, but by using gauge data, we can do a whole bunch of modeling and processes to figure out what the corresponding flood frequency analysis is at a site. So how does this then tie back to these kind of two buckets we're talking about today, site characterization and real-time monitoring? Well, in terms of site characterization, we actually need the flood frequency analysis at a site to then figure out what the magnitude of flood is that would expose the pipeline. So that feeds into that whole process of determining thresholds. And then for real-time monitoring, using the return periods in these quantiles is actually really important for figuring out what's going on regionally for alerting. So this is a simplified explanation, but what I'm showing here is we have two gauges and we have a site. This site doesn't have a gauge on that exact water course that you can see, but we have gauges that are pretty close by. I realize I don't have a scale, but you can see the town of Cochrane's close by. So what we could infer is that if there was, say, a 20-year flood event happening at these two different gauges on different streams, then since Horse Creek is in close proximity, it's likely that there's a flood event going on, potentially a 20-year event as well. So the actual method is a little bit more complex, but that's how we use those return periods for monitoring at a high level. So it's clear that flood frequency analysis and getting site characteristics is really important for our entire monitoring system and hydrotechnical hazard management. And we need to do this for all of our gauges and all of our sites in Cambio. So that's 360,000 sites and 11,000 gauges. And the way that we do that is through the North American stream network that we have at BGC. So it allows us to do flood frequency analysis for all sites and gauges by effectively, one of the core parts of this is by determining the upstream drainage area of a gauge or catchment, so the watershed. And by determining the watershed, then we can get attributes of the watershed like the area and other characteristics like overall relief, to then draw relationships between gauges and sites so we can create that site FFA. But what I'm hoping you can see by this slide is that this stream network is complex. So we have 22 million segments across North America. They all have metadata. They're all directional and connected. So doing processes to traverse up the segments and work with the stream network is challenging. So now I'm going to pass it on to Dr. Patrick Grover to talk about some of the ways we're addressing these challenges and just improving our site characterization and real-time monitoring in general.
Awesome. Yeah, thank you very much, Evelyn. Yeah, so as you can see from the last slide, we deal with a lot of large data sets to support both site characterization and flooding and flood monitoring in Cambio. And working with these big data sets presents significant challenges using the current technology stack which is based on using relational databases, basically SQL databases. Add to this the fact that there's ever increasing amount of new data sets which are becoming available that can really help us with site characterization and flood monitoring. So we really need new tools and techniques and help us make use of this data to develop more advanced statistical and machine learning algorithm and models. We just finished a proof of concept project to explore the use of Databricks, which is a data analytics platform to help us get the processing scale that we want to do the more advanced machine learning and data science work. Databricks is built around a technology called Apache Spark, which is a technology that allows us to run very large queries in parallel on computer clusters. So we can really get some horsepower to do this kind of work. Now, what's great is that the Apache Spark library in Databricks includes support for performing graph or network-based analysis, which is really critical for dealing with that large river network that Evelyn talked about. The library also supports working with geospatial type queries, so working with vector and raster data as well, which is absolutely critical for the kind of stuff that we're dealing with, as well as functionality for us to build, maintain, and manage machine learning and statistical models. Go to the next slide. To demonstrate the kind of performance that we can get from using Databricks, we tested the kind of common query that Evelyn mentioned, which is identifying all upstream segments from a water crossing to form a watershed. So we benchmarked the time to query all of the upstream segments from the Thompson River at the confluence with the Fraser River at Lytton, BC. At this point, the Thompson River is a basin approximately 56,000 square kilometers and is composed approximately about 150,000 upstream segments. Now, using this query using our current technology, which again is a relational database, a SQL Server database, that query took approximately 40 seconds, which is still impressive to pull that much data and walk through the network, but it took 40 seconds. Now, using our river network, but expressed within a graph database within Databricks, the same query took only 0.3 seconds, which is an increase of over 2 orders of magnitude. So that's the kind of scale that we get from adopting these new technologies. All right, next slide. So what will this allow us to do? Well, as Evelyn discussed, one of the important things that we need to do in our hydrotechnical program is to characterize water crossings. And presently, we have a limited ability to characterize the watersheds and the river segments in our system, and that kind of limits the amount of the level of analysis that we can do. Statistical and machine learning models run on data, and so the new platform that we're evaluating, it allows us to more efficiently and effectively characterize watersheds and river segments across all of North America. So that's the kind of scale that we need to do. Now, this can do things like, efficiently generate watershed descriptors. Watershed descriptors are features that describe the watershed in terms of things like the hydroclimate. So what's the annual rainfall within a watershed? What's the annual temperature? Can include things like a breakdown of the land cover, the superficial soils, the topography. These are very important characteristics that we need to put into our models. It can also help us to characterize streams and rivers, whether that be inputs for a hydrological model. But one of the key things that we need to do with a lot of our work in Cambio is determine the flood process type, which is based on calculating the melt-in ratio. Now, currently within our system, we do that, but it's a very expensive query. But within the Databricks platform, we can calculate the flood process type quite quickly, and that will tell us whether or not a river is prone to clear water flooding, debris flows, or debris floods. Finally, we can do more advanced analysis, such as characterizing the drainage network within a watershed. And recent research has shown that the drainage network topology has a significant impact on hydrology. So this is opening new doors for looking into more advanced characterization. Next slide. So what does this allow us to do? Well, I've got 3 examples of work that we've either completed or are currently working on that shows what happens when we have the ability to do better characterization. So currently we're working on a project to implement a more advanced regional flood frequency analysis. As recall, regional flood frequency analysis is how we estimate flood quantiles, like 20-year flood, 100-year flood, 50-year flood, at water courses where we have no gauging information. And this new regional flood frequency model will be developed, that we're working on, will be developed for all of North America and trained using watershed and river characteristics that will significantly improve our flood quantile estimates. That'll help with our site characterization. Now, where things get really exciting is when we combine field inspection data from our Cambio, we can do really interesting things. If we combine those with watershed characteristics and the river network, things get very exciting. So last year, we combined field measurements of changes in the field measurements of the changes in the pipeline depth of cover based on repeat inspections. So you go inspect a site, estimate the depth of cover over the pipeline, come back a few years later and do that again and calculate the difference. What we did was then we combined that information with precipitation data to find precipitation events and characterizations of precipitation events which result in significant geomorphic change. And this results in better precipitation monitoring thresholds for our clients. Finally, and this is a project that we're working on right now, we're combining the field inspection data, again, specifically information about the channel geometry with the river and watershed characteristics to train a random forest model to predict bankfall width and depth. And this will really improve our screening level hazard assessments. And I think the other thing that'll help us do is prevent us from having to visit non-credible sites, because we'll have very detailed, or have a model that will at least predict the channel geometry. So we don't spend time going to look at farmers' fields and what have you. Okay, next slide. So the examples I just talked about were projects that we're working on that were really focused on better characterization of hydrotechnical hazards. And so what's next for us, and what are we starting to look at? And I think that the focus is now, or we'll begin to also start looking at how do we enhance our flood monitoring program. So I've got two examples here. The first one is an approach that we've done a proof of concept a couple of years ago, and this is using a procedure called regional streamflow based frequency assessment. And what this can do is estimate discharges at ungauged rivers. This is an approach that's done by pooling observed stream flows from nearby gauges and using a regression-based flow duration curve allows us to estimate the stream flow at the ungauged site of interest. Now, this approach would greatly enhance our flood monitoring program by providing us more accurate estimates of flows and more confidence in high flow alarms at our sites of interest. The other thing that we're really interested in, and it's actually something we've been working on for some time, is flood forecasting. Flood forecasting is important because predicting high flow events is important to provide time for pipeline operators to take proactive actions to minimize the risk to their infrastructure and to the environment. Data-driven flood forecasting using neural nets and have been shown in recent research to outperform physically based hydrological models and can be applied to a wide range of rivers in a more cost-effective approach. And this is important, particularly in Canada, where we have very limited access to flood forecasts. So yeah, I hope that was interesting. We provided kind of an overview of our systems, and yeah, Evelyn and I are happy to take any questions. And yeah, if you have anything, please feel free to reach out and contact us, and that's our emails up there. Thank you.
I'm not seeing anything in Q&A or chat. So
Thanks, Patrick and Evelyn.
All right, well, thank you very much.
yeah, thanks so much.